Hello everyone, this is Abhishek Mahanti and welcome to lecture number 18 of the chapter Electric Charge and Field. In the previous lecture, we had discussed about the second application of Gauss law, that is to derive the expression for electric field due to a uniformly charged infinite plane non-conducting state. Today, in this lecture, we will discuss about the third and the final application of Gauss law, which is to derive the expression for electric field due to a uniformly charged spherical cell. So, let's get started. So, students, remember that spherical cell means it is a sphere where the interior is completely empty. For example, a football. Football is example of a spherical cell where inside the football there is no matter present. So we have given some charge to this spherical cell, and the spherical cell is uniformly charged. So look at the diagram here. We have a spherical cell and point O is the center of the cell and capital R is the radius of the cell. And suppose capital Q is the total amount of charge given to this cell. So let me write here that capital Q is the total charge on the cell. Total charge on the cell. And since it is a cell, so whatever charge you give to it, all the charges will lie only on the surface. That's why this is the case of surface charge distribution. And what is the value of surface charge density? The surface charge density in this case, the surface charge density or sigma, surface charge density sigma will be how much? The total charge, that is Q, divided by 4 pi r square. The total charge on the cell, which is Q, and the surface area of the cell, which is 4 pi r square. So this is the surface charge density. Now we will find the electric field due to this charge the cell at three different points. The first point is completely outside the cell. Completely outside the cell means I will choose a point somewhere here. The point P is outside the cell, and at this point I will find the electric field intensity. Next, I will find the electric field intensity where? On the surface of the cell, on the surface of the cell. So I'll find the electric field somewhere here at a point which lies on the surface of the cell. And finally, I will find the electric field intensity inside the cell. Electric field intensity inside the cell. I will choose a point somewhere here such that the point is lying inside the cell, and at this point I will find electric field. So total I will do the three derivations at a point completely outside, at a point on the surface of the cell, and at a point completely inside the cell. At these 3 points I will find the electric field intensity, and I have to do it by using Gauss law. But students, before going to the derivation part, let me draw the electric field line pattern due to this charged spherical cell. We know that if we have a positively charged body, then the electric field lines, they are radially outward. So we have given positive charge to this cell. So the electric field lines will be like this, they will be radially outward. So this red arrow mark represents the electric field lines due to this spherical cell. So remember that the electric field lines due to a positively charged body is radially outward. So these are the electric field lines. Now I will do the first derivation. The first derivation is what? It is the electric field at a point outside the cell, outside the cell. So let me choose a point P somewhere here such that the point P is completely outside the cell, and suppose the distance of point P from the center O is smaller. So let me join point P with point O. So this distance is smaller, and since the point P is lying outside the cell, so small r will be definitely greater than capital R, because the point P is lying outside the cell. And I will find the expression for electric field at the point P by using Gauss law. So students, I had told you that whenever you are using Gauss law, you have to consider a closed surface, because if you look at the mathematical statement of Gauss law, it states that the closed surface integration of E dot ds is equal to 1 by epsilon naught times the total charge enclosed by the surface. So you have to integrate E dot ds over a closed surface, and that closed surface is known as Gaussian surface. I had told you that whenever you are going to choose the Gaussian surface, you have to be very smart. And you have to choose the Gaussian surface in such a way that the angle between E and ds, means the angle between electric field vector and area vector, is either 0 degree or 90 degree. So in this case, we have to choose a spherical Gaussian surface. While proving the Gauss law using a point charge, I had also taken a spherical Gaussian surface. Similarly, in this case, we will also consider a spherical Gaussian surface. And the spherical Gaussian surface will have the radius small r, and the center of the Gaussian surface or Gaussian sphere will be the point O. So let me write here that consider a Gaussian sphere. Consider a Gaussian sphere of radius r, Gaussian sphere of radius r, and centered at O. So I will draw a Gaussian sphere whose radius is the small r, and the center of the sphere will be O. So let me draw here like this. This is the Gaussian sphere, and this Gaussian sphere has a radius small r, and the center of this Gaussian sphere is at the point O. So definitely the point P will lie on the surface of the Gaussian sphere. Is that clear? Now we will integrate E dot ds over this Gaussian sphere. So how to do that? So to integrate E dot ds, we have to first find what is the angle between electric field and the area vector. So students, remember that area vector is always perpendicular the surface. So in case of a curved body, you have to choose a small element here. So let me choose a small element here. If I choose a small element somewhere here, then the area vector will be given by outward drawn normal, like this. And remember that if you have a sphere, then the radius of the sphere intersects its surface perpendicularly. So if you want to find the direction of each area element on this Gaussian sphere, you have to draw radially outward vectors like this. At this point, area vector will be in this direction. At this point, area vector will be in this direction. It means electric field is radially outward, and at the same time the area vector is also radially outward, because we have taken a spherical Gaussian surface. So the angle between E and ds is 0 degree. Now the integration will be very easy for us. The closed surface integration of E dot ds will be how much? That is equal to E ds cos 0 closed surface integration. And remember that all the points on this Gaussian sphere are equidistant from this spherical cell, from this charged spherical cell. So at every point on the shell, the electric field will have the same magnitude. That's why I can take this E outside the integration symbol. So E integration of ds, and this cos 0 is 1. So ds means the area of a small element on this Gaussian sphere So the closed surface integration of ds means what? It is the total surface area of the Gaussian sphere. So that will be E into 4 pi r square, because small r is the radius of the Gaussian sphere. So E into 4 pi r square is the left side of the Gauss law. Now we know that according to this Gauss law, E dot ds closed surface integration is equal to the total charge enclosed by this the total charge enclosed by the Gaussian sphere, Gaussian surface, divided by epsilon naught. So we have calculated this quantity to be E into 4 pi r square. So E into 4 pi r square is equal to what is the total charge enclosed by the Gaussian sphere? So you can see that this Gaussian sphere completely encloses the spherical shell. So whatever charge is present on the spherical shell, that amount of charge is also enclosed by this Gaussian sphere. If capital Q, if capital Q is the total charge on the spherical shell, then the Gaussian sphere also encloses the charge capital Q, because this shell is inside the Gaussian sphere. So I can write capital Q by epsilon naught. That implies bring this term 4 pi r square to right side. So you will get expression for the electric field outside the cell, E out is equal to 1 by 4 pi epsilon naught q by r square, q by r square. Is that clear? So this is the expression for the electric field due to a spherical charge, spherical cell at a point outside it. Now just analyze this expression. So we had already discussed about the electric field due to a point charge. Assume that we have a charge q at point O, and there exists a point P at a distance r from it. Then the electric field will be how much at this point P? What is the electric field? 1 by 4 pi epsilon naught q by r square. Is that clear? So this expression is same as this expression, means in this case the charge is distributed over the surface of the cell, but in this case we have a point charge at point O, and this point P is at a distance r. So if we compare these two equations, then we can say that whenever we are finding the electric field intensity due to a uniformly charged spherical cell at an outside point, then the electric field is similar to the case like the entire charge capital Q is concentrated at the center. Means if I place the total charge of the sphere at this point O, suppose the total charge Q is placed at point O, then the electric field at point P will have the same value. So remember that when you are outside the cell, then the electric field is similar to that of a point charge. Means you can assume that the entire charge of the shell is concentrated at the center of the cell, but actually the charge is residing on the surface of the cell. Okay. So this is the expression for electrical intensity outside the cell. Now we'll go to the second derivation, that is to find electrical intensity on the surface of the cell. The second one is on the surface of the cell. On the surface of the cell. So in this case, what will be the electric field? Now if you bring the point P towards the surface, then gradually small r will decrease, and when point P will lie on the surface of the cell, then small r will be equal to capital R. Is that clear? And now if you draw a Gaussian surface like this, having a radius capital R and center at O, then you can see that the Gaussian surface or the Gaussian sphere will coincide with the spherical shell. Is that clear? So how to derive the expression for electric field intensity? Just do nothing. simply replace this small r square with capital R square, because if you draw a Gaussian surface and then if you find the integration of E dot ds, then the value will be E into 4 pi capital R square. In this case, the integration of E dot ds will be how much? It will be E into 4 pi capital R square, because now the radius of the Gaussian sphere is capital R, because the point P is lying on the surface of the cell. And this E into 4 pi r square will be how much? It will be the total charge enclosed by the Gaussian surface, which is again same as the charge on the cell, because you can see that this Gaussian surface is coinciding with the spherical shell. So we can say that the Gaussian sphere just encloses the entire charge of the shell. So I can write Q by epsilon naught, that implies E surface is equal to how much? 1 by 4 pi epsilon naught Q by capital R square, and this is a fixed value because capital R is fixed for this cell. But look at the first equation here. This is the equation 1. Here this small r is not fixed because I have chosen the point P here, but if you want you can choose the point P here at any point. So if we are going outside the cell, then the distance r, the distance small r is variable. But once you are on the surface of the cell, then the distance from the center is always the radius, that is capital R. Okay, so this is the expression for electric field on the surface of the cell. This is equation 2. Now finally we have to derive the electric field intensity inside the cell. Suppose I'll choose a point P inside the cell here, and the distance is small r. So in this case small r will be less than capital R. And again, if you in the same way, if you draw the Gaussian sphere like this, then if you find the integration of E dot ds, then E dot ds closed surface integration will be how much? It will be E into 4 pi small r square. But we know that E dot ds is equal to how much? Total charge enclosed by epsilon naught. But look at the diagram here. This Gaussian surface, this Gaussian sphere does not enclose any charge, because charge is located on the surface of the cell. Inside the cell there is no charge, and we can say that inside the Gaussian surface there is no charge because the Gaussian surface is inside the cell. So this Q will be 0. So 0 by epsilon naught is also 0. So I can write E into 4 pi r square equal to 0. That implies E inside is equal to 0. So we got that the electric field intensity due to a spherical shell at a point inside it is 0. So we have done all the 3 derivations. Now we will plot a graph between electric field taken along y-axis and the distance r taken along x-axis. So electric field along y-axis, distance r along x-axis. What is this small r? Small r means distance of the point from the center O. And suppose this is the point where small r is equal to capital R. This is the radius of the cell, and now we have to draw the graph. So students, you know that inside the cell electric field is 0. So from the center, this is center, from the center up to the surface, there is no electric field. So the graph will coincide with the x-axis. But when you reach at the surface, then the electric field is how much? The electric field is 1 by 4 pi epsilon naught Q by capital R square. So on the surface of the cell you get some electric field. So this is the electric field. This point represents the electric field equal to 1 by 4 pi epsilon naught Q by capital R square. And when you go beyond the surface, outside the surface or outside the cell, then this is the formula, E equal to 1 by 4 pi epsilon r q by small r square. And when you go away from the shell, what happens? Small r increases and electric field decreases, and it decreases according to the inverse square law of distance. So beyond this point, electric field decreases like this. So here E is inversely proportional to r square. So this is the way you can derive all these derivations, and you can plot the graph between E versus R. So students, I hope that you have understood all the derivations, and we have discussed about all the three applications of Gauss law, which is in your NCERT syllabus. And I hope that you have acquired some idea how to choose a Gaussian surface, how to do the how to find the surface integral of electric field over a closed surface. And in the upcoming classes, we will also solve many numericals from your NCERT book as well as from other books. So you have to practice all these three derivations, because these derivations most of the time come in your examination. So please practice all the derivations, and again in the upcoming classes I will discuss about more numericals with more concept. So till then, have a nice day and bye bye.